Assalamualaikum and a very good day. Today I would like to share our research which is entitled Fractional Casson blood flow with gold nanoparticles in a slit velocity cylinder. I'm Wan Faezah Binti Wan Azmi, together with other co-authors Ahmad Kushari Muhammad, Nuruddin and Sheridan Shafi from Department of Mathematical Sciences, Faculty of Science, UTM. Today's presentation we will cover all of this. I will proceed with the introduction. First is fluid. Fluid can be categorized as liquid and gases. There are two types of fluid in fluid mechanics study, which are Newtonian and also non-Newtonian fluids. Newtonian fluid obey Newton's laws of viscosity. As we can see in this graph, it has a linear relationship between shear stress and shear rate. But in this study, we will focus on the non-Newtonian fluid, which is Casson fluid model. Why Casson fluid? Because it has a unique behavior. As you can see in this graph, it can behave like an elastic solid or no flow occurs if your stress greater than the external applied shear stress. Meanwhile, fluid can start to flow or deform if the external applied shear stress greater than the yield stress. It also imitates human blood flow in the small arteries. Next is the heat transfer process that involved in this study is the free convection flow. As we can see here, it occurs naturally due to the differences of the temperature and also density. From this picture, warm fluid is less than the cool fluid. It will rise up due to the buoyancy force. Meanwhile, cool fluid will go down due to the gravity force. Next is the slit velocity. Slit velocity does exist in a real-life applications, and it plays a vital role in studying the variations of the fluid velocity. It occurred at the boundary between two different mediums. Next is a nanofluid. Nanofluid is one of the innovative ideas to improve the heat transfer characteristics of the fluid. It contains metallic nanoparticles with high thermoconductivity that are uniformly dispersed in the base fluid with the low thermoconductivity to produce high thermoconductivity fluid. In this study, gold will be considered as nanoparticles since it has high thermoconductivity and also good biological compatibility. And for the base fluid, it will be considered Casson fluid model as blood. Next is fractional derivative. It discusses the innovation of the derivative if it is a fractional or complex numbers. It has many definitions such as Riemann-Liouville, Caputo-Fabrizio, and Antagana-Baleno. But in this study, we will focus in Caputo-Fabrizio. This is the definitions of the Caputo-Fabrizio. Next is the research aim. The aim of the present study is to investigate theoretically the unsteady free convection flow of the fractional blood model with gold nanoparticles passed through a cylinder together with the slit velocity effect. Next, this picture shows the schematic diagram of the problem. Consider an incompressible Casson fluid flow along the z-axis of the cylinder. R is the radial coordinate which is taken normal to it. R0 is the radius of the cylinder. Yellow color represents the gold nanoparticles. When t greater than 0, fluid starts flow with the occurrence of slit velocity at the boundary of the cylinder. Temperature of the cylinder was raised from ambient to the wall temperature and remained constant. From this diagram, we can come out with the governing equations of momentum and energy. Next, this is a nanofluid thermophysical properties based on theory and test model. Next is methodology. First, we propose the problem and then we derive the governing equation to obtain the dimensional governing equation for the momentum and energy together with the initial and boundary conditions. As you can see here, governing equation for the momentum is first equation and then energy equation is for the second equation. Subscript and F indicate the nanofluid. Next is third equation show the initial and boundary condition. US is the slit velocity. Next is a non-dimensionalization process by applying the appropriate dimensionless variables to obtain the dimensionless form of the governing equation together with the initial and boundary conditions. Here is the dimensionless variables in the fourth. We will apply to the first and second equation to obtain the dimensionless form of the governing equation for the momentum and also energy. From here, we will obtain the dimensionless parameter such as Grashof number. This is the dimensionless form of the energy equation and also initial and boundary conditions. Next, we apply Caputo-Fabrizio fractional derivative model to the both dimensionless form of governing equation, momentum, and also energy. And we obtain S8 and 9. Beta 1 is the constant parameter for the Casson parameter. And this is the definition for the Caputo-Fabrizio fractional derivative. Next is we apply Laplace transform to transform the governing equations with respect to the time together with the inertial and boundary conditions. Okay, as we can see here, 10 is the energy equation of the Laplace together with the boundary condition here. And then 12 is the momentum equation together with the boundary conditions here. Next is we apply finite Hankel transform to transform the Laplace partial differential equations with respect to the radial coordinate to obtain ODE. As you can see here, 14 is for the momentum equation and 15 is for the energy equation. Rn is the positive roots and J1 is the Bessel function for the first kind and first order. Next is we reduce or simplify the ODE and apply the inverse Laplace transform. As we can see here, 16 is the energy equation and then 17 is for the momentum equation. Next, we apply the inverse finite Hankel transform to obtain the analytical solutions of the problem. And then we do a validation, graphical result and analysis. Lastly is conclusion. As you can see here, 18 is the analytical solutions of the fluid temperature. And then the 19 show the analytical solutions of the fluid velocity. Next, I will proceed with the result and discussion. Figure 2 show the validation of the result. We compare with the limiting case of the present result with the previous published result from the Khan et al. And the obtained result is identical with the published result, which means the obtained result is valid. Next is the figure 3. It shows the influence of Casson parameter on the fluid velocity profiles with slip and non-slip conditions. As we can see in this graph, blue color indicate the slip condition and red color indicate no slip occurred. From this graph, fluid velocity decreases with the increment of the Casson parameter. As Casson parameter increases, the fluid viscosity increases and fluid becomes thicker, which resists the human blood flow. Hence, it will decrease the fluid velocity. Next is the figure 4. It shows the impact of the Grashof number with respect to the slip velocity and non-slip velocity conditions on the fluid velocity profiles. As we can see in this graph, increment of the Grashof number will lead to the increment of the fluid velocity. As Grashof number increase, buoyancy force will increase and enhance the fluid flow movement. Next is figure 5. It shows the impacts of the Prandtl number on the velocity and temperature profiles. As we can see here, fluid velocity and temperature decrease with the increases of the Prandtl number. As Prandtl number increase, momentum diffusivity will increase and create resistance between fluid particles. Hence, it causes decrement in fluid velocity. Meanwhile, as Prandtl number increase, thermal diffusivity will decrease and can cause the fluid to cool down faster. Next is the figure 6. It shows the effects of the nanoparticle volume fraction on the velocity profiles and also temperature profiles. Based on the graph, increase in nanoparticle volume fraction will increase the fluid velocity and also temperature profile. It is because thermal transfer rate is increased when gold nanoparticle concentration is increased, which is it will enhance the blood velocity and also temperature. Next is figure 7. It shows the effects of fractional parameter on the fluid velocity and temperature. By increasing the fractional parameter, fluid velocity and temperature increase with presence of slip and no-slip effects at the boundary in a large time interval. Conversely, fluid temperature decreases as fractional parameter increase for small time interval. The differences occur between small time and large time interval due to the memory effect of the fractional derivative. Obviously, it can be seen here, fluid with fractional model is more realistic compared with the classical model. As a conclusion, the unsteady free convection flow of fractional blood with gold nanoparticle pass through a cylinder together with the slip velocity effect has been investigated by using Laplace transform and finite Hankel transform. Second, fluid velocity increases with the presence of the slip effect, Grashof number, nanoparticle volume fraction, fractional parameter and also time parameter, while it is decreased with the increasing values of Casson parameter and also printed number. The temperature profiles increase with the nanoparticle volume fraction and also time parameter are increased, while it is decreased when the printed number increase. And lastly is fractional fluid model more realistic than the classical fluid model. And that's all from me. Thank you.